All right, everybody, welcome to lesson 3.1, exponential functions and their graphs. This is our first of several lessons in Unit 3 on exponential and logarithmic functions. So in this lesson, we're going to cover everything about the basics of exponential functions, and then in the next lesson, we'll introduce log functions. This is something that is part of the Algebra 2 curriculum, but we're going to go into a little bit more depth and make sure that everybody has a solid foundation on this for the rest of our year in Honors Pre-Calc. So here's what we're going to do. By the end of this lesson, you will evaluate and graph exponential functions, and you will use exponential growth and decay to model real-world scenarios. We're also going to look at compound interest specifically in this lesson. Our essential question is, how do exponential functions compare to polynomial functions? You should already know, obviously, what a function is, and we are going to cover the natural base e. This is something that you've learned before, but we are going to review it. And yeah, that's what we've got going on. So let's get started. Okay, so here are the important things that you need to know in this lesson. An exponential function is a function that has some value, some number, which is referred to here as a, to the x power. So this is the first time we're seeing functions that actually have the variable in the exponent. Up until now, all of our polynomials were like x to the second power or x to the third power or whatever. And now we have some number to the x power. And what you will see is that these functions grow significantly faster than your standard polynomial functions. But let's keep going. We are going to use something today called the one-to-one property, which says that if you have two bases raised to an exponent and the two sides of the equation are equal, then the exponents have to be equal as well. We're also going to be looking at the natural base e. In many applications, the most convenient choice for a base is the irrational number e. This is called, or the f of x equals e to the x is called the natural exponential function. Okay, and the last topic that we're going to cover in this lesson is compound interest. And I'll cover more about maybe the specifics at the end of the lesson with what compounding means. Really, it's just like the number of times the interest is added to the account in a year. But all of these variables show up. So we're going to fill in these blanks so that we know what's going on when we have to use these formulas. So A is your current balance. In the account or of your loan or whatever we're looking at here. P is the principal amount. And that means the amount of money that you started with. R is the interest rate. And that's in decimal form, not percent. N is the number of times that we are compounding in a year. And T is the time in years that we're interested in examining. Okay, so all of this is going to help us to determine when we put a principal or an initial amount into an account, or we take out a loan of a certain amount, and then a certain amount of time goes by with a certain amount of interest. There's a certain given interest rate as a percentage that we're going to input in decimal form. And that interest is added to the account a certain number of times per year. Then A will give us the current balance, or how much is in the account now with all of the interest added. So there's all these different little pieces working together for this formula. And continuous compounding means that the interest is literally moment by moment added to your account as it's earned, instead of being added at a certain interval of time, it's like constant. And the formula changes a little bit and uses this letter E, which is one of the ways that this irrational number E is useful. It's just kind of like pi, right? Like it's just something that shows up in application that wasn't really invented. It was just kind of discovered as a convenient choice or as a limit of what something's approaching. Yeah, so we will continue to examine that as we go through these notes and throughout the whole unit. So the first thing we're going to do here in example 1 is pretty simple. We're just going to make sure that you know how to enter an exponential expression into your calculator. Hopefully this is not a big problem. So in example 1 here, we're just going to make sure we do 2, and then this little up arrow caret looking thing raises us to the exponent, and we type negative 3.1. And to the thousandths place means 3 decimal places. It goes tenths, hundredths, thousandths. So this would be 0.117 based off of that. Then we have 2 to the negative pi. And I get 0.113. And I want to point out in this specific example here, please note that just because we have a negative exponent does not mean that the answer is negative, right? 2 to the negative pi is the same thing as 1 over 2 to the positive pi. And so just if our base is positive, so this 2 is positive, it doesn't matter if the exponent's positive or negative, the answer is always going to be positive. There's no way that we can force this to become a negative number. It just depends. All that changes is whether your answer is in the numerator or in the denominator. Okay, and that brings us to example 2. We're going to look at some graphs of exponential functions. Graph each function below and find the requested characteristics. So we're going to start with the graph itself. And what we're going to think about is, instead of using the calculator, I'm going to try to actually plug in each of these x values into this function and see what happens as we graph this. So if we think about 2 to the 0 power, if I'm plugging in 0 for x, 2 to the 0 power, anything to the 0 power is 1. So I'm going to put a point at a y value of 1 for an x value of 0, right? Plug in 0 for x, I get 1. If I plug in 1, 2 to the first power is 2. If I plug in 2, 2 to the second power is 4. If I plug in 3, 2 to the third power is 8. And what you should be able to see here is that every time that we increase the exponent by 1, we're multiplying by an extra 2, right? 2 to the third means 2 times 2 times 2. 2 to the fourth means 2 times 2 times 2 times 2. So it was an extra times 2. So every time we go over 1 unit, our value doubles. And the same thing happens in reverse. Every time we go to the left 1 unit, our value halves. So as we go left from the y-axis here, we're going to be at 1/2, and then 1/4, and then 1/8, and then 1/16, etc. I'm not going to plot all of those points, but you get the idea. The same thing can be seen if we plug in the number. So if we do 2 to the negative 1, it would be 1 over 2. And that gives us that 1/2. So anyway, I plotted all these points, and you can see already by the time we get to an x value of 3, we're already growing really quickly, and this is going to double for every 1 unit until we go to the right. So it grows very fast and very, very quickly. It's almost hard to imagine how fast it's going to double and continue to increase, but it's crazy. It does it. So let's fill in some of these blanks over here. So our domain, the x values that have a y value, is actually all real numbers. You can plug in any number here for this exponent and you'll get an answer. You can see that on the graph as well. As we go left and right, there's no holes or breaks. Everything's going to be included. The range. So the range here, notice there's no negative values. There's nothing down here in the second or the third quadrant. Second or third. Yeah, I think that's right. I'm blanking on the quadrant numbers. Hold on, let me pause for 1 second. I don't want to mess you up. All right, so I was wrong. Quadrants go 1, 2, 3, 4. So this is the third and the fourth quadrant. There's nothing in the third or the fourth quadrant. So for the range, we don't want to include anything down here on the y-axis. And in fact, we'll never even hit the x-axis. So we're going to start at 0 and go up because we've got a horizontal asymptote right there. So we'll never touch the 0. And the y-intercept is right here at 0, 1. These first two parentheses are intervals. This one is an ordered pair, so don't be confused by the notation that looks similar. We do have an asymptote, as I already said. We've got that horizontal asymptote right there at y = 0. And we are increasing for the entirety of the graph, from -infinity to infinity. You can see from -infinity to infinity, this is always going up, okay? Letter B, what happens if we change the base? So if we have 2 to the x first, but now we have 4 to the x, how does this change? So let's take a look. I'm just gonna start plugging in numbers just like before. So 4 to the 0 power is 1. 4 to the first power is 4. 4 to the second power is 16. Okay, so already we had to multiply by another 4 and we got off the page. If we go this way, 4 to the -1 power is 1/4. So it's also shrinking faster over here. So we got our horizontal asymptote. We grow really quickly. There's something on the table stopping me from making that look quite right. But that's going to eventually intersect at a y value of 16 when we get to an x value of 2. So somewhere up here. But you can see it's growing a lot quicker than letter A did. Other than that, though, what you're going to find is that a lot of this specific information is pretty similar. The domain is still -infinity to infinity. The range is still 0 to infinity. The y-intercept is still 0, 1, even though we grow quicker. Anything to the 0 power is always 1, so we're always going to have a y-intercept of 1. Our asymptote is still y = 0. And we're still increasing for the whole domain. So even though we changed the base, we changed how fast we grow, but we didn't change the domain, the range, the y-intercept, the asymptote, or whether we're increasing or decreasing, okay? Okay, 2 more questions to graph. What happens if we change the exponent to negative? So what if we have 2 to the -x? All right, so if we plug in 0, 2 to the -0 is just 2 to the 0, which is still 1. Hopefully that looks familiar. If we plug in +1, we have 2 to the -1, which is 1/2. And what you're going to find is that the whole graph has kind of flipped over the y-axis. So if we plug in -1, we get 2 to the +1. Plug in -2, we get 2 to the +2, which is 4. And then we're going to get 8. So the whole thing flipped around. Looks like that. Our domain is still the same. Our range is still the same. Our y-intercept is still the same. Our asymptote is still the same. And the only thing that's different is that now we're decreasing from -infinity to infinity. And the letter D is going to be pretty much what you would expect. It's going to be just like this one, but flipped. So I'm going to sketch that real quickly for us. Okay, and the answers are going to be the same. All right. So anytime that we make the base higher, we're going to grow faster and faster. Anytime we change the exponent to negative, the whole thing flips. So that's kind of basically the behavior of an exponential function if you're looking at the graph. But now we're going to look at more of the algebraic properties. So let's take a look at example 3. Use the one-to-one property to solve for x. The one-to-one property, as I said at the beginning of the lesson, says that if the bases are the same, you can set the exponents equal to each other. So in example 3, what we need to think about here is how do we make these bases the same? And I'm going to rewrite 9 so that it looks like 3 squared. Because we know that 3 squared equals 9. And once I do that, now I have two sides of our equation with the same base. And I can just kind of think of it as canceling out the bases. We can set the exponents equal to each other using that one-to-one property. And then we can solve for x. I'm going to subtract 1 to the other side. And I get x equals 1. I'm going to do the same thing in letter B, but this one's a little bit trickier. I have options here. I think the easiest thing to do is to think about, okay, I'm not going to want to change the 8 into a 1/2. So I'm going to change 1/2 to 2 to the negative 1. And negative 1 to the negative first to the x is the same thing as 2 to the negative x. That's one of our properties of exponents. That if you have something to a power, you can multiply the powers together. And on the other side, I want this 8 to be a base of 2. And if I do 2 times 2 times 2, I get 8. So I'm going to write this as 2 cubed. And now if I can cancel out the bases, I get negative x equals 3. So x has to be negative 3. Now that is not the only way to approach this question. You could also change the 8 to 1/2 to the negative third, and you would still get that x is negative 3. But that's the general process we want to use there for the one-to-one property. Let's look at example 4, transformations of exponential functions. So let's see. If we have a number added or subtracted in with the x, think about it just like our original transformation guidelines, right? If we have a number added or subtracted, we shift left or right. So this is going to be a shift left 1 unit. If we have a number added or subtracted outside, so at the end of our function, not included exactly where the x is, but just at the end of the function, that's a shift up or down. So this is going to be a shift down 2 units. If we have a negative in front, it's a reflect about the x-axis. And if we have a negative in with the x, it's going to be a reflect over the y-axis. And that's the one that we saw on the front side already when we had a negative in with the exponent. Now, I'm not going to take the time to type all these into my graphing calculator and examine, but hopefully you can see based off of the things that we've learned in the past that this makes sense. And if you want to, you can take out your graphing calculator, type these in, and see how they transform 3 to the x. Okay, well, let's keep going. Example 5, evaluating the natural exponential function. Use a calculator to evaluate each expression, round to the thousandths place. So that's that 3 decimal places again. And this is going to be pretty similar to what we did in example 1. The trick here is just finding where E is on your calculator. So on my calculator, if I press second and then the divided by button, that's where the E is. There is another spot down here with the natural log where it says e to the x. That will, here, let me show you. If I press second and then natural log, that has an E with an automatic exponent. But if you use the other E button and then press the little up arrow caret, it also makes an exponent. So either one of those works. Well, let's see, let's try this. So we're gonna do e to the negative 2. So we get 0.135. If I do e to the negative 1, it should be 1 over e. 0.368. E to the 0.25. 1.284. And e to the negative 0.3. 0.741. Okay. Hopefully that wasn't too bad. And that brings us to 2 different applications. We'll start with compound interest. A total of $12,000 is invested at an annual interest rate of 9%. Find the balance after 5 years if it is compounded, quarterly, monthly, or continuously. So let's try this. So we've got a couple different numbers given. What this is telling us, if we take a look at the beginning of our notes, we're going to be trying to match those numbers up with these variables. So the $12,000 is the initial amount that's invested. So that's going to be, in other words, the principal. So P is going to be 12,000. We have an annual interest rate of 9%, so that's R. So R is going to be 0.09. Remember, R is the decimal version of the interest rate. And 5 years is the time that's going by, so that's T. And the time is always in years, so it's nice that it told us it in years. And so we have the P, the R, the T, and let's see. We still need the N. So in this first question, if the interest is compounded quarterly, what that means is 4 times per year. Quarterly would be like once every 3 months. So that's 4 times a year. So that means that our N, which is the number of times compounded in a year, is going to be 4. So let's just do this one before we move on to the next one. So for this specific question, we have N compoundings per year. So we're going to use the first formula from the front. That looks like this. And notice we have this exponent with variables in it. That's giving us, that's the reason that we're doing this in this lesson. It's an exponential function. It's an exponential application. So let's see. The A is going to be what we're looking for. We're looking for the balance. So we're leaving A blank. P is 12,000 times 1 plus R over N. So R was 0.09. N was 4. And the exponent is going to be N times T, and T we said was 5. Okay, so we plugged in the P, the R, the N again, and the T, and we're going to type that into our calculator. When you do that, make sure you focus and get these parentheses correct, and make sure the 4 and the 5 are in the exponent. And once you do that, you will end up with a rounded amount of $18,726.11. All right. In letter B, we have the same scenario, except instead of compounding quarterly, we're going to compound monthly. So in that case, the N is 12. Now let me clarify something here. Your interest rate is telling you what percent of your balance are you going to earn per year, right? So we would get 9% of this added to our account in a year if we were only compounded once at the end of the year. But that's not exactly what happens. So when we compound quarterly, you don't get that full 9% every quarter. You get like 1/4 of your yearly interest rate after a quarter. And that's kind of what's going on in this formula, is we're multiplying the amount by 1 plus the interest rate divided by the number of compoundings. So instead of getting a whole 9%, we're going to get 9% divided by 4. And then we're going to get that multiplied by our initial amount, however many times we're compounded total. So it's going to be 20 times because it's 4 compoundings per year for 5 years. It's kind of breaking down what this formula is doing. So if we are compounding 12 times per year, we're adding the interest to the account 12 times per year. It doesn't mean we're getting 9% every month. It means we're getting 1/12 of the 9% every month. But what you have to realize is that you want, if this is like a amount like that you're investing, that you're going to earn money on, you want more compoundings, because as soon as something gets added to your account, now that's being included in the initial amount for the interest to be earned on the next time that there's compounding. So in this first scenario, after 1 quarter, there's interest added to our account. Now our 9% is a little bit bigger because we have more in our account, right? So let's just work through this formula. So for letter B, almost everything is going to be the same, except we have an n of 12 instead of 4. To the 12 times 5. And if we type that into our calculator, we will end up with 18,788.17. And hopefully it makes sense to you that we earned more money because their interest was added to our account sooner so that we can earn more interest. Yeah, okay, so let's keep going then. In letter C, we are compounded continuously, which means the interest is added to our account moment by moment as we earn it. And so for this specific scenario, you might think of n as being infinity, right? We're compounding infinite times per year. We're not going to try to plug in infinity into our formula. Instead, we have an alternate version of the formula that uses e. So it's a equals p e to the rt. So let's plug in here. So p is still 12,000. E is E, that's already a number. We don't have to plug in for E. And then R is 0.09, and T is 5 years. Okay, so we multiply that out, and this time we get a total of 18,819.75. And notice that the number went up again. And sometimes people think, well, if we're compounding continuously, then we should end up with infinite dollars. That's not exactly true, right? Because even though the interest is being added to our account moment by moment, it's still only by the end of the year going to be 9%. And that 9%, what the 9% is of, increases a little bit over time as the interest that we earn slowly gets added to our account. But it still doesn't mean we add infinite dollars, right? It's still 9% over the course of the year. So that's how compound interest works. Hopefully that makes sense. You've got those two formulas, and you use one formula when you have a specific n, and you use the other formula when you're compounding continuously. Example 7 brings us to radioactive decay. The half-life of radioactive radium is about 1,599 years. And what that means is that every 1,599 years, the amount remaining is split in half. So what this says next is after another 1,599 years, 1/4 of the original amount will remain, and so on. Let Y represent the mass in grams of a quantity of radium. The quantity present after T years would be Y equals 25 times 1/2 to the T over 1,599. Letter A, what is the initial mass when T equals 0? Well, Y is the mass. So what we need to do here is plug in 0 for T. And so this is going to be 1/2 to the 0 power, which is 1, times 25 is going to give us 25 grams. So in these types of questions, the number in front of the 1/2 is usually the initial mass. And then in letter B, how much mass is present after 2,500 years? Let's try it. You plug in 2,500 divided by 1,599. And if you plug that into your calculator, you're going to get 8.458 approximate grams. If you, yeah, no, that's good. 8.458 grams. Yeah, you chemistry people might think that we need to focus on our significant digits, which is fine if you want to do that. I'm not going to be picky about that because that's not one of our topics, but technically, since we had 2 significant digits originally, I suppose we should use 2 in our final answer. But there we go, okay? So let's just kind of check that. So if we started with 25, 2,500 years go by. That's definitely more than 1 half-life, and you can see that more than 1/2 of the initial amount decayed, right? Went away. Okay, cool. So that is the end of the notes. The worksheet should be fairly straightforward for this lesson, but let me know if you have any questions, as always. And thank you very much for watching.